Hello, my name is Woojin Lee, and today I will talk about our work on virtual wire, supporting rapid prototyping with instant reconfigurations of wires in breadboarded circuits. This is joint work with Ram Krishna Prasad, Sung-Woo Jae, Yoonji Kim, Ian Oakley, Daniel Ashbrook, and Andrea Bianchi. Virtual wire is a novel tool for prototyping circuits that allows users to insert components on a physical breadboard and to connect them without physically placing wires. Instead, users can design the circuit layout using computer software, such as Fritzing and Autodesk Eagle, to specify virtual wires that describe how components should be connected. With the popularity of electronic prototyping platforms, circuits are now commonly created and built by a broad spectrum of non-technical makers and academic researchers. For such users, assembling circuits by placing wires and components into breadboards remains a challenging and time-consuming activity. The key problems of breadboarding are both simple and fundamental. Components are misplaced, wires are omitted, connected incorrectly, or inadvertently disconnected. Novice and intermediate users have reported that such errors are hard to diagnose and debug. These issues remain an obstacle for exploring breadboarded circuits and contribute to the notion that the activity is intimidating and confusing. Researchers have previously proposed techniques to simplify breadboarding by focusing on qualities such as speed and ease of building the circuit, supporting increased complexity, and the use of novel substrates. A notable work is CircuitStack, which places circuit topology on swappable conductive sheets clamped under the breadboard. However, making changes to the circuit topology remains laborious, involving redesigning and printing the sheets along with disassembly and reassembly. Other works, such as Vizier, aim to ease the physical construction of circuits, but did not support arbitrary multiple wire connections. You may refer to the paper for more detailed information on related works. Virtual wire's reconfigurability is enabled by a switching matrix, which allows unlimited arbitrary connections on the breadboard, which is instantaneously recognized and reflected in hardware, without needing physical rewiring or disassembly and reassembly. To establish the appropriate size for the breadboard, we extracted metrics related to the size and complexity of circuits of typical Arduino projects in two common maker resources, 15 from the Arduino project book and over 4,000 from the online Fritzing projects repository, which yielded an average of 12 electrical nets. Based on the small size of the circuits in the repositories and in line with prior work, we selected a breadboard with 16 rows, or 16 unique electrical nets. During the use of virtual wire, as connections are placed or updated on the designated software, the virtual circuit layout is automatically updated on the physical breadboard in real time, producing real electric connections matching the virtual ones, creating a fully functional circuit. The final circuit design can be saved, shared, or automatically prepared for fabrication as a PCB. The prototype breadboard can be detached and immediately used in conjunction with the fabricated circuit. Virtual wire can be used in a myriad of different ways. The basic process of creating new circuits with both analog and digital components are enhanced through the use of virtual wire. Here's the circuit that controls a microserver motor using a potentiometer and external power source. Also, a sound level visualizer circuit that uses a dual operational amplifier and low-pass filter. These examples were taken from the Arduino Starter Kits projects book and an online maker community's repository respectively, and emphasizes the involvement of processes such as reading analog data, hardware filtering, and PWM output. The user can also easily explore alternative hardware configurations. An example of this would be the reconfiguration of logic gates as shown here using a NAND gate chip. A more practical example would be the use of digital modules that support complementary features such as different communication buses. Virtual wire also supports rapid and seamless adjustments, allowing for the potential to optimize specialized subtasks, such as picking component values among a set of alternatives. For example, we show a case where a low-pass filter is tuned by adjusting the values of the resistors and capacitors in its RC network. Virtual wire integrates with existing design and fabrication tools. For example, it can also serve as an ISP chip programmer tool. Shown here is the Virtual Wire's internal Arduino setup as an in-system programmer for the Atiny 85 microcontroller. We conducted two separate studies to evaluate the efficiency and experience of using virtual wire as a prototyping tool. The first study was a performance-based quantitative study. It compared objective measures of performance between virtual wire and traditional breadboarding conditions by tasking the participants with the assembly of 4 different circuits of varying complexity with each of the 2 conditions. Participants could submit their circuits multiple times until it was submitted correctly, and errors were logged and organized as either self-detected errors or at-check errors, and whether it involved missing or misplaced wires, end components, or inverted components. The second study was an interview-based qualitative study. After a brief demonstration of virtual wire and a warm-up session with the system, participants were asked to build 3 circuits of various complexity. They then compared these sessions with their prior experience in building circuits. Virtual wire led to statistically significant reduced task completion times. No significant difference was observed between the mean of checks requested in the virtual wire condition and the mean of checks requested in the breadboard condition. Statistical analysis of error counts showed that virtual wire also led to significantly fewer errors. We have plotted the duration of each trial and highlighted the times where self-detected errors and at-check errors occurred. The shorter task times and reduced number of at-check errors in the virtual wire conditions are immediately evident. The statistical analysis along with the visualization supports the claim that virtual wire can improve not only the speed with which novice users can produce breadboard circuits, but also the accuracy and correctness of their work. It is especially worth noting that virtual wire reduced the number of at-check errors. We suggest this type of error in particular is challenging for a user to detect and debug during real-life circuit creation, where it is hard to know when errors were committed, which components they involve, and even whether it originated in software or in hardware. All participants praised the system's ability to reduce the clutter and fragility of physical breadboards. Most participants noted that virtual wire integrates well with normal prototyping workflows rather than disrupt or change practices. Participants speculated on several possible applications for virtual wire, including educational training, testing components and sensors, and exploring different variations of a circuit. Please refer to the paper for more information on the results of both studies. Some points of discussion before wrapping up. The results of the study revealed possible integrations of virtual wire within more layered environments beyond circuit prototyping and designing. One such application being an educational setting where the onboard Wi-Fi microchip can be used to publish wire instantiations to all personal devices across a classroom. The use of cross-point array chips to implement the reconfigurability makes its integration with previous related works, such as Virtual Component, which similarly uses cross-point array chips, easier. Alternative modes of implementation may also be explored, such as with FPGAs, which are programmable logic block hardwares. However, if FPGAs only work with digital signals and require expertise in combinatorial logic and are not beginner-friendly. The final direction of exploration would be the use of added assistive interactions. As it stands, virtual wire does not indicate the correctness of the circuit topology or detect the correct placement of components. That's all for this presentation, and thank you for listening.